Okay, so thank you very much for the introduction. I'm Daniele Contessi, and today I will tell you something about the detection of Berezinskii-Kosterlitz-Thouless transition using generative adversarial networks. So, okay, maybe this one. Yes. So the task we intended to tackle is the detection of phase transitions for many-body systems. So basically what we want to do is to find the arrangement of the phases of matter with respect to some control parameters. And we want also to basically detect this diagram here, for example, the points where the system goes from one phase to another phase at equilibrium. So it's not the dynamical phase transition that we were seeing before. Yes. So we know that phase transitions can be both classical and quantum, depending on the nature of the fluctuations that drive the transition. And also we know that there are very good methods that can give a very interesting understanding and insight about the physics, like in a phenomenological way with the Landau-Ginzburg method, and also in a more systematic way with the renormalization group. And the common aim of these already existing methods is to explain what's going on along a phase transition and try to explain the origin of this universal behavior along a phase in the vicinity of a critical point. And our intention is instead to develop a method, a data-driven method, which is automatic and is able to map out the phase diagram of a many-body system, both classical or quantum. And we want to use machine learning for that. So let me rephrase a little bit what is the challenge. So we have this, suppose we have this parameter space spanned by these gamma 1 and gamma 2 control variables. And we have some data representative of our many-body state at equilibrium, and with the triangles and squares, I indicate different underlying structures in this data that can also be hidden to the naked eye if you want. And we want to find with a machine, we want to teach a machine recognize these different structures in this data, so we can actually divide these two regions of this parameter space. And this was already done in several ways, both with supervised method, so by mapping this problem to a classification problem, so just assigning different labels to different underlying structures in your data, and also with the unsupervised method. So we wanted to develop something which is unsupervised, and so we used this the so-called anomaly detection protocol, which is an already well-known technique in the machine learning community. So basically we have you have a data set containing some normal samples and abnormal samples, and you want to train a model so it is able to reconstruct only normal samples. And so the model can then report if there is some, after the training, some abnormality in the data you're feeding to the model itself. And so the result after the training can be like this. So you have this input data, which is the left picture, let's say, and the reconstructed data. And for those data which are normal, the reconstruction is almost perfect, while for abnormal data, it cannot reconstruct anymore. The key ingredient for this is the so-called autoencoder, which is basically a lossy compression from an original also highly dimensional space to a latent space, which is low dimensional, and back to the original space. So at training time, what you do is that you train your autoencoder by minimizing a score function, a loss function, in this case the so-called reconstruction function, reconstruction loss, sorry. And so after the training, your autoencoder will be able to correctly reproduce all the input data that are normal, let's say. Instead, it won't be able to reconstruct the anomalies. And by measuring this reconstruction loss, we can have an idea about the anomaly score. It's the so-called anomaly score. So we can have an idea about how much is this anomaly big, let's say. And actually what we did was to add another network for the training, which is the so-called discriminator. So the whole network now it's a generative adversarial network. And basically the training now it's adversarial, so it's done in a competitive way between the autoencoder and the discriminator. So the autoencoder tries to fool the discriminator that must distinguish between fake examples and real examples. The real examples are the one from the database, and the fake examples are the reconstructed data. And in this case, you have to minimize 2 losses at training time, but then in the end, at test time, if you want to detect anomalies, you just use the autoencoder that was trained with this adversarial procedure. So just a few words about the input features that we used to tackle our problem. So the input features must, in our case, at least embed the changes in the physics along the transition, otherwise your method won't be able to detect the phase transition. They must be general and as model independent as possible, and also you should inject the lowest prior knowledge about your system. And so we chose the degree of quantum correlations, or the measured with the bipartite entanglement. So basically we can simulate one-dimensional systems with the tensor network, and we have access to a reduced density matrix, so we can divide our system in 2 subportions, and we can compute the reduced density matrix for one of these 2 subsystems, and look at the distribution of the eigenvalues of this reduced density matrix. The minus log of this distribution is just the entanglement spectrum, and has already been shown to contain a lot of information about with complex structures, and also degeneracies and symmetries, and even information about the topological order. So, okay, coming to the results, we have these 3 one-dimensional quantum systems on a lattice at 0 temperature. And for what is common for these 3 systems is that they have a BKT transition in a region of their phase diagram. The BKT transition is very subtle because the changes in the thermodynamical quantities are very smooth. So there is no, let's say, discontinuity in the thermodynamical quantities. And so it's very difficult to detect in general, also with traditional methods. And the GAN in our case is trained only in one of the phases of these systems, and the gapless phase in particular. And so basically all the other phases are anomalies for our machine. And for this case, for example, this is a benchmark. A model that we use as a benchmark is the XXZ model. The technical details are not important. The location of the critical point is known because this model is analytically solvable, so we can use it as a benchmark. And we have 2 phases in particular for our analysis, the paramagnetic phase and the antiferromagnetic phase. We we trained our GAN with the entanglement spectra from one phase with different configurations spanned by these control parameter delta. And then after the training, when the reconstruction loss is minimized, we can feed then the autoencoder with the entanglement spectra from the other phase, and the result is that the reconstruction loss rises in the vicinity of the transition point. And also, it depends on of course, on the system size. So this goes in the right direction. So toward the thermodynamic limit, this increase becomes much more steep. And so what we did was to apply this method also to other models. So the Bose-Hubbard model, where the transition is known only from numerical simulations. And the two-component Bose-Hubbard model, we only have an estimation of the phase transition in this case, of the location of the phase transition in this case, and it's still debated in the literature. So to conclude, we proved once again that the entanglement spectrum is a good feature for the detection of phase transitions. Also, we showed that the generative adversarial network can really improve the performances of a simple autoencoder training that was already used in other works in the literature, and the detection of the BKT is in agreement with the values we find in the literature. I just want to say that this method is not meant to compete with traditional methods according to the numerical precision of the phase transition, but it's very agnostic about your data and so on, so it can be used to find out and map out your phase diagram. And now we want to use more sophisticated architectures and also apply the same scheme to other input features, because you can also use not only the entanglement spectra as an input feature, but in principle, whatever feature and data that you like. And with this, I thank you for the attention, and I'm open to answer to any question.
Thank you very much. So do we have some questions for the speaker? Well, if not, then I will maybe start. You can think of your brilliant question that's been bugging you, but you were too shy to ask. So my question is the following. With all those phase classification methods that rely on training on some specific part of the phase space, there is always the possibility, for example, that you actually had two phase transitions somewhere over there, right? And you only trained, let's say there were three phases, and you only trained on one of them. So, would you be able to actually notice by your anomaly detection that there should have been two phase transitions, or you would only see, the first one, but the one that you trained against everything else?
I mean, for example, we already tried to apply this method also to the extended Bose-Hubbard model, which has more than one phase transition. So these were just examples, but yes, what you can see is actually that the level of the losses changes according to the phase transition. And so also the rise in the loss changes depending on the nature of the phase transition. So for example, for like second order phase transitions, you see that there is really an abrupt rise of the loss. And so you can distinguish between different phase transitions.
So you would be able to, let's say, pinpoint that there were, let's say, 2 or 3 phase transitions,
yes,
even though you trained only one?
Yeah, of course, because I expect that the loss would increase and then increase again along the second phase transition.
Okay, thank you. Well, if there is no further questions, then let's thank Daniele.
Thanks.